Okay, guys, this morning is going to be our third lecture, and I should start by showing you guys about this one. When you increase the force, okay, if the force point out of this sample is going to be in tension. However, if you do the compression, is going to cause this kind of failure. Okay, in this study, we are going to consider the structure which is going to be large enough when it's subjected to the compression, it won't get the buckling. Okay, that is the first thing. And the material is a kind of steel, aluminum, which called homogeneous and isotopic material. And then when you pull this element, increasing the force, and what you can see is going to be the tension that's caused in this material is going to be increased also. And you may remember the stress occur due to this tension force is going to be normal stress, or is going to be tensile stress. When you increase the force larger and larger and larger until one point, it's going to be high. Into one point, the material separate. This is called the failure of the material. And you can see the failure of the material didn't occur on this large portion. It occur on a small portion because normal stress is equal to force divided by the area. When the area is small, the force divided by small area gonna cause large stress. And the stress over here is going to be larger than the stress over here. Okay, because the area over here is large. That's when the stress large enough to break the paper is cause the failure of this paper. Okay, the first concept. Do you understand me? Please answer me. Can you understand this concept? The next concept is going to be this one. Okay, if this one is very strong, we will consider the failure of this paper. This kind of failure different from the previous one. And you can see the failure in the theory. They said the failure is going to do due to the shear force, and the line of failure is not really in the straight line. It's going to be in the inclined line. But the inclined line going to produce large area. So theoretically, this kind of failure is, they said, is going to do the shear force that's going to separate this part of the paper from the rest of it. And since the shear force going to occur on the surface, unlike this one, the normal force occur perpendicular to this. This is called the normal stress. But due to the force that's parallel to the tearing portion, this is called the shear force. And this shear force produces the shear stress. Okay, we may have the force pushed into this. And since there is two surfaces, the shear force, for example, if this is 10 Newton, the shear force that's causing on the two sides going to be 5 kilonewton. And then you divide 5 kilonewton by the area here. You get the shear stress. And large shear stress also cause the failure of the material. And I should show you the failure of this thing are different. The failure over here is due to the normal stress. the failure over here is due to the shear stress. Any question? No one gonna ask me question? Thanapon, you're going to sleep again, right? And then let me start the PowerPoint. Thanapon didn't turn on the microphone. Let me start by this one, okay? And I should say, if the structure or this one is a kind of aluminum specimen, and then it hold on the top and on the bottom, and you can see when the load increase, when the force over here increase, you're going to produce the stress. That's going to be the force divided by the area. And you can see the failure occur in this portion. It didn't occur in these two portions because the A over here is minimum. When the A over here is minimum, is produce the maximum stress in this area. Okay, and then when you draw this free body diagram, in the reality, the force P over here, okay, is going to be in the axial force and produce this normal stress. And this normal stress is computed by this equation. Okay, when it's large enough, it causes the failure of material over here. Okay, this kind of failure is called necking. Okay, and then there is another type, the bolt over here. The bolt over here subjected to a single shear, okay, occur on this way. This is going to call the single shear because the failure path is only one here. Okay, it's going to be in the structure that connected like this one. Okay, and then you have the bolt that's connect the top portion and the bottom portion together like this. Okay, and then this bolt going to subjected to the force in this direction, and this bolt going to subjected to the force in this direction, and there is one plane or cutting plane, and this called single shear. If the force here is going to be shear, okay, this one going to be shear force, and you can see if you cut only this portion of the bolt into consideration, there is going to be the shear force occur on the surface of this one. Okay, and if this one V, this one going to be V, and the tau is going to be V divided by the area here. Okay, and you have this one used to compute the shear stress. If the stress is very high, okay, if this one is high, it's going to cause this failure. And if this one is high, it's going to cause this failure. The failure occur in the material, okay, it may be occur in the structural member such as this one, or it may be occur in the connection such as this one. This is the example. I show this one, the experiment over here, and this kind of picture. I like you guys to relate your experience with what you are learning here. That's going to enhance your understanding. Okay, now come to the real structure. There is a number of structure that you may consider like this one. Okay, and then you may say this member may call the log. Okay, for a general name, you may call it tension member. Okay, and in a more general one, you may call this one two force member, or a more general one, you can call this one axially loaded member. There is a number of terminology that's called only this portion. Okay, the simple thing is this structural member is going to be in tension, and if you just draw its free body diagram, you may take this one out of their support, and you can put the force is going to be axially loaded force pull into it. Okay, and the force over here gonna be the tension force, and then when it's subjected to this tension force, this is going to have elongation. Okay, and also if you take a more deep considering of this, you can see the force that occur in the rod will transfer to the plate over here. Okay, the plate over here. This one we call it connection. The connection is going to connect the structural member, which we may call it the rod, to the support. And you can see the support over here has the pin that go to this portion. And for this one, if you like to dock it, you may dock it like the pin here, and this one will be the connection that's connect if you put it into two dimension. Okay, this one maybe connect to this ball, and then has the lot over here, and the force applied over here. Anyway, the lot, okay, connected to this middle portion. Let me put it into the light bulb. That is going to be big steel plate. Okay, there is a steel plate over here. Okay, by doing this, if this is 10 kilonewton, this one going to be 10 kilonewton, and then the green bolt over here, okay, will be subjected to the forces, okay, basis upon this. You may say the force that's applied over here will act over here. The force going to be 10 kilonewton over here, and then the resistant force due to the lead portion of this one will be like this. Okay, if this is V, this is V, you may have the summation of F sub y equal to 0, 2V equal to 10 kilonewton. So each V going to be 5 kilonewton, and the cutting plane of this bolt is going to be 2. So we call this one as the double shear. Okay, this is double shear. The same as this one, if you consider it by the same principle I just mentioned, this one is going to be in double shear. There is a lot of application of this kind of lot and this kind of connection in the real world structure, as I show you over here. Okay, any question? No question. Okay, if you no question, I will go further. When we learn about this subject, we have the normal stress equal to the normal force divided by the area. Okay, this will be the normal stress, and we call this as the sigma normal stress. And we also have the another equation tau for the shear stress. Shear stress is going to be shear force divided by the area. And then the problems that involved with this equation, there are 3 of them. Okay. The first one is a direct one. If you know the dimension of the connection or of the structural member, what it means is you know this area, you know this area, okay, you know the dimension of the structure. And also, if you know the F-high force, when you know the F-high force, what it means is you may use the free body diagram and you use the equation of equilibrium. You may determine the normal force. You may determine the shear force. And then the problem, the first type is 1.8. You just find the stress at some specific points, okay, by using this equation. Now, for the second one, this equation may be right in the other way. You may write is P equal to normal stress times A, or you may write it to be V equal to shear stress times A. Okay, the next one, the problem is going to be determine the largest load that can be applied to the structure. What it means is you're going to determine the force P, the force V, and for the force P and the force V, you use the free body diagram and the equation of equilibrium to determine the applied loads. Okay, that is going to be usually the maximum applied load. By doing this, they're going to provide you with the area, okay, of the structural member, with the cross-sectional area of the connection, and they also provide you with the allowable stress. What it means is this one, the sigma over here will be the sigma and then allowable. This one going to be tau allowable. Why? Because usually the structure will subjected to unexpected forces, and it's also may be subjected to the corrosion. Usually when we use the material in the construction, in the manufacturing of car, in the manufacturing of airplane, we're going to apply the factor of safety to make it safer. Okay, for example, for the steel, it's going to be 200 megapascal divided by 2. That is going to be 125 megapascal. And again, you also have the tau allowable for the steel is going to be tau sub y divided by factor of safety. This is going to be calling the yielding shear stress. Okay, this tau sub y, you may have this one from the lab. Okay, you may get it by testing it based on the standards such as Thailand Industrial Standard. And this one also, we call it actually just short as the yielding stress. Actually, it's going to call yielding normal stress. They just take the normal out and call it yielding stress. We're going to have this one in chapter 3. Okay, we will discuss this one later. But for this one, Ajahn will provide you with this value, or Ajahn may give you to compute by basis on this equation. Now, you will find P and V, and again, you may find the largest load that can apply to the structure. The last way of using this equation, okay, is to call the analysis. The last way we call it the design. In the design, we just rearrange the equation again. In the design, it means we are looking for the size, the dimension of the structure or the dimension of the connection. So by doing this, the A, okay, going to be the one that we are looking for. So A is going to be equal to P divided by sigma allowed. And by this way also, we have this A equal to V divided by tau allowed. By doing this, they are going to provide you the allowable stress. You know this one, you know this one. And then again, you use the free body diagram and you use the equation. You determine the V, you determine the P. So by doing that, you can determine the dimension of the structure. There are three types of them. That you guys must be able to solve these three types of problem. Okay. Anyone have a question on this slide? Again, no one, right? No one going to give me any noise, any sound, any question? Kulitikong. Any question? Lisa?
No answer.
No? Are you still sleeping? Lisa? Lisa just sent in my invitation to be her friend. Natapong.
Yes, good morning, Ajahn.
Good morning. Okay.
Yes,
Can Fs be huge, like 20? If you design the nuclear power plant in some hard object, such as the portion of the reactor, you may use very large factor of safety. Again, if you are working in the airplane company or the automotive company, which going to build the efficiency airplane and very good car, most of the time the factor of safety is going to be low because they're going to make the airplane as light as possible in order the airplane will use less fuel, but it must be strong enough to taking care of the high wind forces acting on the airplane. So it's up to you as the engineer to select the proper factor of safety when you analyze or when you design the structure. And actually, you got to consult with your senior about this kind of factor. In civil engineering, there is the design code by the government to specify the factor of safety to be used in the design of high-rise building, in the design of the bridge. Okay, I answer you guys, right? Charles? I'm solving this problem with just a lot and beam, but I keep on getting two-digit factor of safety. Oh, yes, in the homework, you get very large factor of safety. I just intend to keep that way in the homework. Okay, so don't be surprised. Okay, that means you guys have a lot of safety for this kind of structure. Thank you very much, Charles. You are a good student. Okay, next we come to the same problem that I have last time. I think I go too fast for this problem. Some of you guys may not catch this one. Let me again. This is going to be a problem of a structural member, this one, and it is supported by the link ABC. Okay, by the link ABC, it means this is the A. and this is going to be the B, and this one is going to be the C. And as you may know, the steel plate AB has the 9 millimeter thickness. This one on the top, this one 9 millimeter thickness, and each one of the plate BC has 6 millimeter thickness. Okay, and then it's connected by the epoxy. Okay, let me stop sharing this one a little bit and show you guys about this connection. Okay, this is going to be the ABC. The bow on the top is bigger than the bow on the bottom. Okay, the problem said the top portion AB only one plate, 9 millimeter thick. The bottom has two plates, that is 6 millimeter thick. And then this plate is connected to a bow at A, to a bow at A, just a bow at A. So this one is going to be in, if it is in the room, it's going to be very good to ask you guys walking around and asking you, what is going to be what? In what? Single or double shear? It's going to be single or double shear? It must be in single shear, right? And then you have another bolt that link into the bottom portion, the red pen. Okay, the red pen subjected to two plates. So the shear that occur on the red pen is going to be double shear. Okay, and the member ABC here is going to be two force member. Is going to subjected to tension. The tension will produce normal stress in the member AB and in member BC, and it's going to produce the shear stress on the top bow with the single shear and bottom bow with a double shear. And also, if you consider more on this portion, it's going to have the bearing stress occur on this area of the hole. Okay, and if you may be able to just build this kind of sample to make your understanding of this problem again. Let's see, this is going to be our problem. Okay, the first steel plate AB on the top, 9 millimeter thick, and BC two plates, each of them 6 millimeter thick, and the groove over here is 40 millimeter long, and the pin at A, the pin at A 9 millimeter. This is big. Okay, the top one is big. The bottom one is smaller because it's 6 millimeter. Shear stress at pin A. Shear stress at pin A is going to be single shear. Shear stress at pin C is going to be in double shear. And then the member A, B, and BC going to be in tension. And then it's going to subjected to normal stress. They ask us the maximum normal stress going to occur in which portion, okay, the green or the yellow. And then they ask us about the average shear stress occur on the epoxy groove. And the last one, they ask us to determine the bearing stress occur at point C. Okay, one time I teach this one, and I use this picture, modified it, and ask you as the midterm examination. So many times you will see the same picture, but not only the question appear here. There are also questions that Ajahn can ask you. Anyway, this one, you are looking for the stress, both normal stress and shear stress. This is shear stress, normal stress, shear stress, and bearing stress. That means the problem is going to be analysis 1.8. Now, we come to the problem. Okay, they give us what? Sigma equal to P over A. They provide us with various dimensions of the structure. So, under the application of the force, you guys gonna looking for the internal forces occur on the plate and occur on the connection. We're going to use the free body diagram and the equation of equilibrium. Now, we draw the free body diagram. Before we draw the free body diagram, the connection at A may consider as the pin. The C also consider as a pin. The member A, B, C connected by pin. Between pin, there is no applied forces. So we call this as the two force member, okay, from the engineering static. And if you know this is a two force member, you may draw the free body diagram easily. Okay, I forgot about this one. Okay, we also discussed about this. Okay, this is single shear, this is double shear, and this is double shear. And for the free body diagram, the A, B, C gonna be subjected to tension force. Okay, under the 2,400 Newton, there is going to be two forces at the D. Why? Because this is going to be multi-forces member. Okay, that's why the connection at D has the D sub X and D sub Y. But the ABC, as the definition of two force member, it has only F sub AC. And then the point is, what is going to be the F sub AC due to the 2,000 Newton over here? You have three equations, right? When we consider this kind of free body diagram, we usually use the summation of moment equal to 0. At what? At the point of maximum unknown, to eliminate D sub X and D sub Y out of the equation of equilibrium. So taking the summation of the moment at point D equal to 0. And by doing this, the unknown F sub AC will rotate in this direction, and 2,400 Newton will rotate in the opposite direction. So they said, if you rotate this way, it's going to be positive. That means clockwise is going to be positive. Since this one is clockwise going to be positive, F sub AC will time the distance here to produce the moment. This is going to be 240 millimeter. So this one positive F sub AC times 240 millimeter. And then the moment arm of this 2,400 Newton, which produce the negative moment. The moment arm is going to be this distance. This is going to be the 360. Now you can determine F sub AC easily, and it's going to be in tension. Okay. Next, the shear state at this point. We know this is going to be single shear, right? Yes. And we know that the rod, okay, at this point will subjected to this one. Since this one is 3,600 Newton, by the third law of Newton, okay, this 3,600 gonna apply over here. And then the bolt, okay, that attached to the support will produce the shear force. And by doing this, the shear force over here is going to be 3,600 Newton. And the area here, okay, of the lot is the circular lot. You may compute it by pi diameter square divided by 4, or you may use the pi times the radius square. Okay, which one you prefer? Just use it. Now we have the tau sub A equal to 3,600 Newton pi r square, and then you know that it's going to be Newton per square meter, and Newton per square meter is going to be megapascal. So that's produce the tensile stress. Sorry, the tensile shear, the shear stress of 56.6 megapascal. And usually this one must be less than the tau allowable to check whether it's going to be safe or not. And tau allowable for the steel, that is going to be usually 125 megapascal divided by 2, or it's going to be 62.5 megapascal. That means this one is safe. Okay, the shear stress occur over here is less than the allowable shear stress. Next, we come to the pin C. The pin C is here. Okay, on this one, the pin C subjected to double shear. Okay, and then the 360 Newton will be received by the shear stress on these two sides by summation of f sub y equal to 0, and set the downward is positive. You have 2V equal to 3,600 Newton. So V is going to be 1,800 Newton, half of it. And then this has the 6 millimeter. So by doing this, 1,800 Newton divided by pi and then r squared. Okay, and then you get tau sub c a little bit larger than the tau allowable. Okay, larger than tau allowable of the steel, which is going to be 62.5 megapascal. So this way, you got to change the lot at point C. You cannot just use the structural steel. You may change the material into tau allowable of the high strength steel. Okay, it may has the maximum shear allowable. Sorry, it may have the maximum shear stress of 200 megapascal divided by 2. That is going to be 100 megapascal. By doing this, you just change the material. You just change to a more higher strength. The structure is going to be safe. If not, it's going to be not safe or no K. You got to change it. You are the engineer. Okay, just specify a new type of material used in this problem. Next, we come to the normal stress. Now, this member is going to be in the tension. And again, by doing this, there is a number of things that you're going to consider. You're going to consider the stress for the green one occur over here. And also, since there is a bow, the normal stress also occur on this one. Okay, let me put this one in 2 dimensions. That's Ajahn just show you. Okay, this is going to be the member and glue it at this portion. On the gluing portion, you don't worry about it. It's going to be very thick in this portion. In this portion, it's going to be very thick. So is out of question. Okay, it can take large normal force. And again, over here, there is a 9 millimeter hole. This one, the D sub A is going to be 9 millimeter. Over here, the D sub C is going to be 6 millimeter. When this one is subjected to the force, okay, the force will apply over here and also will apply over here. Okay, that is going to be the stress that's going to occur on this portion and also on this portion. For the green one, when you compare it, as you may see from the failure of this one, okay, for this one, when you pull it, it's going to failure occur on this portion. See, it's not occur over here. It will fail at the hole, okay, the bigger hole. What happened is this one going to be the one that's going to fail. It's going to have a larger stress than this portion. And then we move to the next portion. The same consideration. The normal stress in the BC portion may be determined from this one and from this one. And the stress that's control on this portion will occur here. Okay. And then this one will subject to the same force. This one going to be 3,600 Newton divided by this one going to be 3,600 Newton divided by what? By the area over here. Okay, by the area over here. This one is going to be by the area over here, and this one going to be divided by the area over here. What is going to be the area over here? Okay, by doing this, you may consider this plate is going to have the width. Okay, if you remember it, it's going to be what? I cannot remember the width of it. It's going to be 40 is here. 9, 6, 40 long. Okay, what is the width of this one from this problem? Plate AB 9 mm, BC 6 mm, attached epoxy, determine this one and this one. Hey, oh, this one is 30 millimeter. Okay, it's 30 millimeter. Now we come over here. This one, when you dock it, is going to be, let me draw it like this, on this portion, just draw only this portion. What we have is, this one is 30 millimeter, okay, and over here is going to be 9 millimeter. So the area that's going to taking the stress will determine from this one, okay, and then time the thickness of this. So the area here is going to be 30 minus over here 9, and then time this one 9 millimeter, okay. And on the bottom, you may see this one, there is two plates over here, and then it has the same 30 millimeter, okay, and this one is going to be 6 millimeter. So the area that taking care of this is going to be this portion. So the A over here is going to be 30 minus 6 and time this one, time 12. Now you can see that this one is going to be 21 times 9. This one is going to be 21 times 9. But this one is going to be 24 times 12. This is going to be smaller. Okay, this one is going to be smaller. So sorry for this, it's in Thai. I didn't check it yet. Since the plate AB is thinner, the green one is thinner and has a bigger hole. So the green area is going to be smaller than the yellow area. So the green area, the stress in the green area going to be larger. Okay, if you not consider this, you just do the same way as I did over here. Okay, and then you just compare the stress that's due to this one. Okay, it's going to be 3,600 Newton divided by 21 times 9 square millimeter. That is going to be megapascal. Or if you come over here, okay, the stress is going to be 3,600 Newton divided by 24 times 12 millimeter square. That is going to be megapascal. And you can see this one will be larger. Okay, by following this consideration, you got sigma at A. Sigma at A is going to be over here larger than sigma at C, C, and then the answer is going to be 19.05 megapascal. Okay, and usually this one will be less than sigma allowed. Sigma allowed of the steel going to be 250 megapascal divided by 2.0, which is going to be 125 megapascal. So this one is okay or is safe. Okay, if you trying to compute for this one, just do the computation of it, and then you got this one 3,600 divided by 24 and divided by 12. This one going to be only 12.5 megapascal occur over here. So this is the way of consideration that is going to be a little bit complicated to make you get the etching skill to consider the structure in a simple way. This is a simple one, okay? And then there is the groove that's connect the plate AB with the plate BC, but the groove has two sides, two of them on the left and on the right, on the left and on the right, okay? And then this is the portion that's you glue it, and the 360 Newton formation of F sub y equal to 0, and then this one actually you may use this as the V, okay? And you have 2V equal to 3,600, so V is going to be 1,800, okay, occur over this area, okay? And the shear stress is going to be 1,600 times this is 30 millimeter, this is 40 millimeter. You get the stress on the epoxy to be just 1.5 megapascal. So the polymer engineering, you guys maybe develop a new type of glue that has very high strength, and then you got to has the tau allowable that's going to be larger than this. That means you're supposed to develop the glue with the tau, okay, the tau maximum, the strength maybe 3.0 megapascal in order the shear stress occur over here is less than less than the tau allowable. And then come to the bearing. Okay, the bearing, actually the bearing stress supposed to be occur in this area. Why? Because when we talking about the bearing, the failure is a kind of clutching. See, the clutching of the plate. First, it's not tearing yet, it's just a clutching of the plate. Since the plate is too thin, if the plate is too thin, it may cause this kind of bearing. Bearing, usually, if we consider it, is supposed to be in this red area. But to make it simple, they just use the diameter of this hole, represent the failure area. So, since pin C objected to double shear, so the force applied to this light purple area is going to be 1,800 Newton. And then the area here going to be 6 millimeter thick plate and 6 millimeter diameter of both sides. So that is going to be 50 megapascal. Again, this is a little bit less than the sigma allowable. So this is going to be less than the sigma allowable, which is going to be 125 megapascal. So this one is okay. This type of problem is called the analysis 1.8. Any question from my student? It used to be the examination 2 years ago, if I remember it. Okay. Okay, Natapong, are you sleeping?
No, teacher.
No, okay. Can you follow my lecture?
Yes.
I come back because I'm worried about the last lecture that I go too fast, and I'm afraid you guys may miss it. So I spent nearly an hour on this problem. Okay. Lisa, are you all right? Lisa is sleeping, right?
No.
No,
John, I'm still here.
Okay. Lisa,
Like
you from Cambodia, right?
Yes, John, I'm from Cambodia.
Okay, yeah. I think I just accept you are to be my friend on the Facebook.
I don't think so, John.
You don't think so? Really? How come? Maybe another Lisa. Okay. Lynn, are you okay with my lecture?
Yes, John.
Okay. Let me go next to the more difficult one. Okay. The analysis 1.b. The analysis 1.b is another thing. This time, they ask us to determine the force P that's going to be able to apply to this structure. When we're talking about this structure, they're going to combine this connection with this aluminum block. Okay, the support. And for the simple way of chapter 1, we will not consider the beam AB. The beam AB will be considered in chapter 6. Okay, chapter 6. Okay, we will talking about the beam AB. Now, we assume the beam AB is very strong. Okay, it can be very capable of taking care of the force P. Now, there is two things. The first one is the lot. The lot is made by the steel, has the failure stress of 680 megapascal. Okay, and then we have the block or the bar that support over here, that is going to make by the aluminum. This one, the symbol over here indicate the material. This mark made by aluminum. Okay, and ST over here indicate this one made by the steel. By doing this, that is the pin. Okay, the pin that connect the bar, the rod to the beam and the support over here. The pin must subjected to the shear stress. So they give the maximum shear stress of the pin of 900 megapascal. This is very large. And then by doing this, this is the steel rod. Okay, this is the aluminum bar, and this is the pin. What so-called is the rod has 20 millimeter diameter. So you got to read the problem carefully. And then aluminum has the area over here of 1,800 square millimeter. So this one may be the block. The block is maybe in, if we look it in 3 dimensions, this may be a short aluminum column, and the area over here is going to be 1,800 square millimeter. And then they said the pin at A and C, the grid, okay, has the diameter of 18 millimeter. So the radius of this one is going to be 9 millimeter. Okay, the rod, the rod always has circular section if not specify the other way. Okay, by doing this, they're going to ask the P maximum that can be applied to the structure without failure. And they said the factor of safety is going to be 2. Why? Because this one is not allowable. This one is not allowable. This one is not allowable. We got to change it, divide it by 2.0 to make the allowable stress. And then, since this one connected by pin, and there is no forces between the top pin and the bottom pin, we call this member AC as the two-force member, axially loaded member, tension member. Okay, and then the allowable stress for the steel 680 times 2, that is 340. The bar aluminum is going to be 70 divided by 2, 35 megapascal, and the pin 900 divided by 2, 450 megapascal. The pin is going to be, this one going to be very, very high strength, very high strength steel. Okay, that is going to be, also this one is not a normal steel. Normal steel has the sigma allow is going to be 250 divided by 2, that is going to be 125 megapascal. That is steel in civil engineering. This one very, very high strength steel. Now, what we have the same thing. We going to determine what? We going to determine the force. Okay, we have sigma equal to force divided by A. So the force is going to be sigma A. So we're going to use the stress over here times the area that's given over here to determine each type of force. And again, this is not direct P. This is going to be the internal force that's occurred in each member. And by doing that, let's see, we're going to determine the relationship between the force over here. This is external force, okay, and related to this internal force, we're going to use the free body diagram and equation of equilibrium. Since AC is the two force member, so the force as AC is going to be here, and then at the block, okay, there is the F sub B occur on the aluminum, and F sub AC occur over here. Let me put this one. F sub AC is going to apply to the rod, and this one will be applied to the aluminum box. Since the force in the horizontal direction is 0, for this one, the equation going to be automatically correct. I call it autocorrect. Okay, so we have two more equations left. Summation of F sub y equal to 0 and summation of the moment equal to 0. You may first take the moment at B. Okay, by doing this, you can determine F sub AC. The F sub AC will produce the moment by timing this distance is going to be 2 meters, and then the moment occur around this one going to be clockwise. This is going to be clockwise, and the force P going to have the moment arm of 1.25 is going to produce the moment counterclockwise. So by doing this, the summation of the moment of B equal to 0, counterclockwise going to be positive. So P times 1.25 is going to be positive, and F sub AC times 2 is going to be negative. Okay, we can do nothing. This is going to be our first equation with two unknown. Another one, summation of F sub y equal to 0. Or if you don't like it, you just take moment at point A. You also can use this one instead of summation of F sub y equal to 0. You won't use it, you use this one. Okay, by doing this, the same thing occur. By doing this one will produce the moment in this way with the moment arm of 0.75. And now this is clockwise rotation. This is going to be negative. Okay, P times 0.75. But this one going to time 2, F sub B times 2, and rotate in this direction, in the counterclockwise direction. So it's going to be positive. What we have here is what? We have the unknown of 1, 2, and 3. And we have only 2 equations. Okay, what we're going to do? We cannot solve these 2 equations directly. Since we cannot be able to solve it directly, you got to do the trial and error. Okay, that's why it's hard. So we have 2 equations with 3 unknown. We cannot solve these 2 equations directly. We will use trial and error. By using trial and error, we're going to determine the Pmax for each cases. Okay, and then we will compare for the lowest. Ajahn, how come you compare for the lowest? We are going to find the Pmax. I will explain that later. Okay, let's see. First, we have the force in the rod AC. Okay, we have the force in the aluminum block, and we have the force in the connection, the bolt. The bolt subjected to shear stress. The rod subjected to normal stress. Aluminum box subjected to normal stress. Okay, so there are different kind of stresses. Now we start by the rod AC. Okay, the rod AC, I put it in the blue, has 20 millimeter diameter. By this way, just taking the rod AC. The rod AC subjected to F sub AC. Okay, and this is going to be F sub AC and F sub AC, and stress occur in the lot AC will equal to F sub AC divided by A sub AC, and this one is going to be the equation that we use to compute A sub AC is going to be pi times 10 millimeter square. So this one we know, okay? And then sigma sub AC is going to be the allowable stress. This one will change to sigma allowable of the lot or the steel. Okay, that's we has compute from the previous slide over here, 340 megapascal. So by doing this, we just put this one into this form. So F sub AC is here. It's going to be the allowable stress of the steel and times the area A sub AC. You put the number into it. Okay, it depends on which way you compute. Okay, you may compute 340 Newton per square millimeter. Okay, this is going to be megapascal, and then you may times this by pi, and then times 10 millimeter square. Okay, which way you like, just do it. Okay, but you got to be very careful about the unit. And then for this lecture, I recommend you to do this computation. It's going to be easier. The answer going to be in the Newton. Okay, so by compute this one, you get this one 106.8 kilonewton. What it means is, if you like to produce the failure, okay, at the lot, the P over here must be 106.8 kilo. No, not yet, not yet. The P is going to be computed by this equation. You're going to find F sub AC, right? So the F sub AC is 106.8. So from the equation 1, you put this one, you put 106.8 over here. You can compute for the P. So this is a not direct answer. It's the force that's caused the failure of the lot. It's not the P. You put into number 1, you got the force P. Okay, by doing this one from the equation 1, F sub AC over here, we know 106.8. Okay, and then P over here, P over here equal to F sub AC times 2 divided by 1.25. You got this one for 171 kilonewton in order to make the lot AC cause the failure here. Now, that's the first one. There are going to be 3 of them. Okay, this is the lot failure. Next, we come to the aluminum block. Okay, this one is going to be the aluminum block. We consider the failure of this one. Again, this one is going to be sigma of what? Of F sub B equal to the force over here. The force over here going to be F sub B divided by A of aluminum. This is going to be A of aluminum. Okay, so you may write it to F sub B, and then this one will change to the sigma allowable that we have, and this one is going to be the A aluminum. So by putting this one, you may get this one to be if you may prefer 35 Newton per square millimeter and times 1,800 square millimeter. You may get this one, okay, in the unit of Newton, and you may rearrange it into kilonewton, and okay, and this one supposed to be 63,000 1000 Newton, and then the answer is here. So you cannot use it yet because this is going to be the stress that caused the failure, 63.0 Newton, causing the failure of the aluminum block. But it's not be the force P yet. You got to go back to the equation of equilibrium. You go to the equation number 2. Now, your F sub B is going to plug into this equation and rearrange it. Okay, so you have P equal to F sub B times 2 divided by 0.75. So the second one, to cause the failure of the aluminum, the force P is going to be 168 kilonewton. It's not finished yet. There is the pin that connect the rod to the connection and the beam. Okay, and you can see by taking a look at this, this is going to be single or double shear. This is going to be single or double shear. Keng Lee, actually in this picture,
Single shear.
single shear. Okay, single shear. Since this one is the single shear, that means what? That means the stress that occur on this bolt. Okay, on this bolt, you got F sub AC, right? The stress occur on this one must be F sub AC also. So by doing this, the shear stress, okay, will be F sub AC. Now, we have the tau equal to shear divided by A. And we will be tau times A. And the A is okay. The A can be computed based on the diameter here. The top and bottom, they are equal. Okay. And then what happened is the tau is going to be the tau allowed. Okay. And that is going to be the shear. That is going to be 450 Newton per square meter. And then times pi, this one, hey, something wrong. This is 9 millimeter. If this is not 20, if this one is supposed to be pi r square, this one going to be 9 square. Okay, please check this one for me. It's supposed to be 18 millimeter. Let me check. Okay, this is going to be 18 millimeter, not 20. Okay, to get the answer of 114.5. Okay, change this one. And then you got this one for the F sub AC, right? The answer is not yet obtained. We're going to determine the P. The P that's caused the failure of this bolt. Okay, you just plug 1.5 into this one. So the P is going to be F sub AC times 2 divided by 1.25. You got this one, 183 kilonewton. Now, you have 3 value of the P. Okay, you have 3 value of the P. 183 for the failure of the bolt, 168 failure of aluminum box, and 171 is the failure of the rod. Which one going to be the answer? The P Mech, in which the structure can resist without failure, is going to be which value? You may compute this one, you get the total of this answer, and total score of this is 8. But the last one is another 2 points. It's very important. Which one? Lisa. Oh, many people answer me. 168, the lowest one. Why? Why is the lowest one? Why is the lowest one? Thanapon is going to be the lowest one. Lisa said it's going to be the lowest one. Why? Why is going to be the lowest one? You're going to find the P-Mech. See? And then why you answer the lowest one? See, guys, you are looking for the P-Mech. Why you answer me the lowest one? Thinking about this one. This is a way of engineering thinking. When you load the structure, okay? When you load structure, the P, the value of P will increase from 0 to 10 to 50 to 100 to 120 to 150 to 160 kilonewton. And then when it's reached 168, what happened is the block here fail. The block over here fail. The aluminum fail. When the aluminum fail, the structure fail. Okay, so the answer, Lisa, is correct. We select the lowest one by using this reasoning. The load start from 0 and then it's going to increase continuously until it's reached this minimum value. The block here fail, the structure fail. The answer P-Mech is going to be the minimum. Do you get what I'm saying, guys? Thanapon ครับ
Yes, sir. I just see an answer wrong.
Understand what I'm saying, right?
Yeah.
You see, okay, thank you very much. Anyone have this kind of problem because it's important? การพิชา Marquez,
Yes, Ajahn.
การพิชา is okay, right?
ค่ะโอเคค่ะ
เข้าใจนะฮะ หนูเข้าใจว่าอาจารย์อธิบายว่าอะไรเนาะ โอเค Marquez.
Yes, Ajahn.
Okay, P-Mech is going to be the minimum of these three. Okay, if everybody okay, I supposed to stop a lecture for 5 minutes and then we come to the next problem. Okay, if again a little bit more, if P is acting on the beam AB is 100 kilonewton, just this one, you get the answer of this one already. And then they may ask you a little bit more. If this P is not 83, it's just 100 kilonewton, what is going to be the factor of safety? So the factor of safety is going to be 168 divided by this 100. So the factor of safety is going to be 1.68. If the force is only 100, the structure can take 168. The factor of safety is going to be 1.68. Okay, right? So สิริพันธ์ครับท่านอาจารย์ไหมครับ
ค่ะ
You can catch me, right? Warwick, catch อาจารย์ right?
ครับผม
Okay, let's us break for 5 minutes. Okay, and then we will come back to the next problem of the design. Okay, go to have water and I will come back later. Okay, อาจารย์ come back. Okay. Student, I like you guys to use a lot of things nearing you to represent or to make you more understanding, like a rubber band. When you pull a rubber band get elongation. There is the normal stress occur on this rubber band. And then if you pull it with very large force, finally, the rubber band will fail. Okay? Engineer has most of the time, the basic thing that you need to do is first, you analyze it. Does structure or that connection is safe or not? Okay, that means you already have the structure. You just must check, analyze it to check it. It's going to be safe or not. Another way, you don't have that structure. You design it, you create it, you build it. Okay, that is going to be the problem about the design. And then if you like to prove the shear, you may apply the force to the spring like this. Okay, my hand that's pulling the spring cause the shear stress inside it. Or very simple, just use your hand and make it like this. Okay, and if anybody has some accident and slide on the floor like this, you may get the wound, okay, from this force. Since there is the friction that's caused the shear force to your skin and make the wound into your face, something like that. That is the shear stress. If the shear stress is too large, again, it's caused the wound. It's caused the failure of the material. Okay, that is the basic thing. Let me go a little bit further to the design. Now, we come to the important thing for the engineer. In the design, that means we're going to use the equation that we have from what? Sigma equal to internal force divided by A. We're going to require to determine the A, okay, by putting the A into this side, and then we divide P max by allowable stress. That means we will use this area. So it depends. If the member is going to be square, sorry, it's going to be round, the A required will be pi r square. If it's going to be like square like this, so the A required maybe if this one B, it will be B square. If the member have rectangular section, okay, the A required will be, this is B, this is H, it may be B times H, and usually they said H equal to 2B. So this one will be 2B squared. So most of the time you got to determine the radius or diameter of the rod, okay, and also you may determine the radius of diameter of the rod, and don't forget about the structural member that has square or rectangular section. Now, by doing this for the shear also, we have tau equal to shear divided by A. So this is the area that's used to taking care of the shear stress. That is going to be shear maximum divided by tau allowable. In the same way like this, the sigma allowable or tau allowable, if the problem specify already like this, you don't need to divide it by factor of safety. Don't do it, okay? This already be uses, okay? Unlike the previous one, you got to compute sigma allowable and tau allowable. Now, you know this one, you know this one, you're going to determine the area. So from the structure, you got to use the free body diagram again, and you use the equation of equilibrium to determine the Vmax and Pmax. So please, going back, review your engineering static, okay, to make you guys have a deep understand of this, because if you determine wrong Pmech and wrong Vmech, then the answer you are looking for is going to be wrong also. Okay, so go back to review your engine static. Now, consider this structural member is going to be the frame, and this frame has the connection at C. This kind of connection is going to be double shear. Okay, why? Because the cutting plane over here, there are two cutting planes. Okay, and then they asked us to determine the size of the pin at this point by taking the tau allowable of 55 megapascal. And then there is a member over here. That is going to be two forces member over here. And they just asked us to determine the area, the area by using the sigma allowable of 120 megapascal. Ajahn, how about the other part of it? This one, if possible, they may ask you to determine the sub B. And then they said, if this one is single shear, what is going to be diameter here? Or they make you a little bit further, find D sub A. If this one is double shear, it's going to be different. So this is a simple one that you have in the example. A lot more may ask you further. So many times you may see this kind of problem in the examination, but they ask you the author question. Okay, so make sure yourself, you guys is very capable on the engineering static. Now, we're going to draw this one. This is going to be two forces member. This is going to be pin. The pin at C will have C sub X and C sub Y. And the force over here going to be only F sub AB. So by doing this, this is going to be our free body diagram. Okay, apply force 15 kilonewton. This one 25 kilonewton. This one only F sub AB. And this one will have C sub Y and C sub X. Now, by doing this, we are going to find the F sub AB for the lot AB. And we're going to determine C sub X and C sub Y. But C sub X and C sub Y, not really the resultant force. In this problem, when you got C sub X and C sub Y, you will find the resultant force at C equal to square root C sub X square plus C sub Y square. This one going to be the force that apply to the pin over here. Okay, it's going to be the resultant force of C sub X and C sub Y. Now, taking the moment at C. By taking the moment at C, you can see that 15 gonna produce this kind of rotation. And this force is going to be 25. And since it's in the vertical direction, times 3 over 5 and rotate in this direction. By using this rotation point, F sub AB will be in this direction. And then they said clockwise rotation is positive. So F sub AB times 200 millimeter gonna produce the positive moment. Okay, and this one 15 times 75 millimeter. If you prefer, you got to change it into millimeter. That is going to be produce the negative moment. this one 25 times 3/5 times this length is going to be produce the negative moment. And we also has this one 25 times this one 4/5. This produce no moment because the line of force cut at point C. So you got this one and this one, and finally very carefully put everything into your calculator. You get F sub AB equal to 15 kilonewton. Okay, now you got to find C sub x and C sub y. Summation of x sub x equal to 0 by putting in this direction. So C sub x is negative. C sub x is negative. Okay, and this one, the same in this direction, is going to be positive. And F sub AB in the same direction of C sub x is negative. So you got C sub x equal to 5 kilonewton. And then C sub y. The summation of x sub y equal to 0. So this guy is going to be positive. 15 is negative. This one is negative. You just put this one, you got C sub x equal to 30 kilonewton. But C sub x and C sub y just component of the resultant force at C. You got to determine the resultant force. Okay, and if I like to say what is going to be, if you doing something like this is going to be vertical, right? C sub x in this direction, and then C sub x is only 5, C sub y is larger, C sub y is going to be 30, so it's 6 times larger. This is C sub y. So in combination, by using the parallelogram, okay, you will get the resultant force that occur over here. This is going to be the R sub C. And if I ask you about this theta, can you find it? This theta going to be tan inverse times what? Times C sub y divided by C sub x. And let's you guys to practice on this. What is going to be the angle of the resultant force R sub C? So you got the R sub C to be 30.41 kilonewton and at the pin C with the double shear. Okay, since it's double shear, that means the shear occur on the pin gonna be half of this one. So summation of force equal to 0, 2V equal to 30.41 kilonewton. So V is going to be 30.41 divided by 2. That's maybe 15.205 kilonewton. And then you have this one, 15.205 kilonewton as the shear, as the maximum shear that occur at point C. Now, based on the equation that we have, we're going to determine the A, right? So by doing this, A equal to shear divided by tau allowable. You may compute basis on kilonewton unit, or if I recommend you, I said you may use this one in Newton, and then divided by the tau allowable. Tau allowable is going to be 55 megapascal. It's going to be 55 divided by this one. So by putting this one, N will cut N, and this one will be millimeter square. And then if you put this one, it's going to be 15205 divided by 55. That is going to be 276.45 millimeter square. And if you prefer, you may know that 1000 millimeter is 1 meter. If you like to find the area, just square it. So by this one, you have the converter 10 minus 6. This is 10 power 3. Number 2, this is that mean 10 power 6 millimeter square. Just time it by 10 minus 6. You get the answer of in the unit of meter square. So it depends on which way you like. Okay, you may put on the top if you prefer, or you may use the same as the textbook. And then since this is the lot is circular, okay, it's going to be pi r square or pi r square is going to be pi d over 2 square, or it's going to be pi d square over 4. And then you may compute the diameter of it. There is a point when you go to Home Pro, maybe, or you may go to the store. The diameter of the lot that sell in the store may not be 18.8. You may see the diameter may be 18.0 millimeter or 20.0 millimeter. Let me ask you guys, which one going to be the answer when you go to the store? Which one you going to buy? 18 millimeter or 20 millimeter? Thank you. The answer comes from Charles. Okay, why? The bigger one, Lisa. Okay, I got the answer. So you got to select the bigger one, right? You got to select the bigger one when you decide it. You're going to answer the 20 millimeter. Thank you very much, guys. The answer is 20 millimeter. The spear selling in the market has certain standard diameter. Okay, and then for the lot, okay, we have the F sub AB equal to 15 kilonewton. Again, the allowable stress is here. We're going to determine the cross-sectional area equal to this one divided by sigma allowed. It depends on you guys. I may recommend you just put this one into this unit if you prefer, and this one divided by 120 per millimeter square. So this one will be in the millimeter square if you prefer. It's going to be 15,000 divided by 120, and it's going to be 125 millimeter square, or it's going to be 0.125 meter square. So please do the unit conversion very carefully. About the unit conversion, please do it. Use the unit, because a lot of students get the correct answer, but the unit is not correct. And then you're going to get the full score. When you use the wrong unit, you may get only half of that, because the unit going to be important, because when you go to the store, you got to give them the value and the unit. Okay, 125 meter square is very huge compared to 125 millimeter square. Now, again, if the lot is the square, okay, that means it's going to be B, and B like this. You may determine the B, okay, to be 11.25. What is going to be? It's going to be B square. It's going to be 125 millimeter square. So B is just square root 125. That's going to be 11.2 millimeter. Or you may compute like this, but I don't like to. I like this one. Just follow the textbook. Okay, and then you select the larger section. That's going to be the design of your structure. Okay, and that's not the end of chapter 1. That's not chapter 1, because actually we have the chapter 2. Okay, I already sent to you already. We have another 5 minutes. Let me show you the chapter 2. So you guys will study it at least and come to my class next time. You will have the idea what will going to be. In the chapter 2, next lecture actually next lecture. In the next lecture, Ajahn will not go directly to the chapter 2. Ajahn will come again with the review of this kind of 3 types of problem. Why? Because this is the main thing for the learning outcome. You guys must be know. And I will show you for one picture. Every one picture, we may decide the problem to be one point A. Okay, and you will also can be modified it into the design. Okay, and we also can be modified into one point B. Just one picture. They also can design the examination to be 3 types of problem and asking you the same way I just showed you before. So next lecture, I will focus, I will pin this kind of skill to you guys again. Be prepared for the examination, build your engineering skill. And when we finish it, okay, we still have some more problem for you guys to practice. And for this one, and I also have some extra thing. And you can see this one used to be the examination. I will put this one, and I don't think I will have time to lecture on of this. By later, I will, maybe before the examination, I will show you how to solve this thing. Because this trimester, we don't know yet. The problem is going to be written like this example, or it's going to be multiple choice. If it's written examination, I will come again and demonstrate to you guys about how to write the problem correctly. But anyway, if you read textbook or you do the homework, please use these examples as your example to do your homework. And then I will, this is homework, I will go a little bit further to strength. The strength is related to the deformation of deformable body or the structure. You know that steel, aluminum, they are deformable material. When the structure built by deformable material, they are deformable structures. Okay, and that is normal strength, and then the shear strength. What I'm saying is actually the normal stress will produce the normal strength. Shear stress will produce shear strength, and normal stress, like this picture, is going to be the deformation divided by its original length. The L is going to be original length, but the shear is going to be another thing. Like I show you guys about the sponge. when you move the sponge, you may see the angle here used to be like angle. When you hook it like this, the angle will change. So this one will define just pi over 2 divided by theta pound. Or if you draw the picture, you just draw my sponge over here, okay? And then if you use the shear over here, it will cause the deformation of the sponge to be in this shape. Usually, the angle over here will be theta pound. This is going to be the angle. And then this is going to be the shear strength. Okay, that's all I have for today. And I hope you guys catch what I teach you. And also, Thank you very much for your attention.